Hi everyone, welcome back. Today's challenge is a really interesting challenge. So we will be solving a gyrus, and then at the end of the video we will be trying to solve Novozybersk, which is this one. So basically Novozybersk has the same idea as Addis Ababa, which is just a string format vulnerability. And for today's vulnerability, I think it's a really interesting one. So this challenge, which is a jars, took me 2 days to solve because I was mainly focusing on reverse engineering, a function that we have used a lot, especially when working with C. And yes, I really had fun solving that challenge. So before I start just solving the challenge, try to solve it on your own as always, and then just came back and have fun with me, I think. Yes, so we start exploring the challenge. So we have overview. So this log contains to all new Log ID Pro account manager. Okay, and the details. So what do we have? So there are no accounts set up on the Log ID Pro account manager by default. So an administrator must first initialize the log with user account and their pins. And user accounts are by default not authorized for access, but can be authorized by attaching the account manager authorizer. Okay. So this prevents users from adding themselves to the lock during its use. Okay, interesting. So yes, so this is the hardware version D and all of that. So if we try to run the program, what do we have? So we had to give an account in order to have access to the door, I suppose. So for example, I'm gonna be sending ironbyte as the username, and as a password, I'm gonna be sending ironbyte 123, and I think the password is not correct. Okay, so let's try to reverse engineer back the code statically and check out what this code can do. So yeah, I have just copied all the code in here. So if we go and check out the main function, so we go to the main, check the main. So the main is basically just initializing the stack pointer as always, and then he's calling the login function. And after doing that, he's stopping the program execution, which is a pretty common thing that we have so in a lot of microcorruption challenges. Now, if you try to go and check what the login is doing exactly, so the login is saving first the two registers, which are register 11 and register 10, and then he is moving 16 to the register 15. So basically, he is moving 16 to the register 15, and then he's calling malloc. Okay, so for those who do not know what malloc is, if you remember the video that um, where I have explained exactly the data structures that we will be using, for example, when dealing with a computer or when interacting with a computer. I don't know if you have watched that video on the reverse engineering series, but malloc is where exactly dynamically allocated data um, is put. So basically we use malloc to dynamically allocate data. So the data returned by malloc is dynamically allocated, which means that it will be living in something called a heap. Um, for example, if you try to create a variable when you are coding, for example, let's suppose you are coding code in C, for example, such as I don't know. For example, let's suppose you are just creating a variable called x, which have a 10. So this x is basically gonna be allocated in the stack as we have so in the reverse engineering videos. But if you, for example, try to allocate some data, let's suppose you are gonna be creating a pointer um, that points to a character, and then you're gonna be doing the malloc and just allocating, for example, 4 values, 4 bytes of data. So those 4 bytes of data are gonna be allocated inside of the heap. They are not gonna be allocated in the stack. So this is basically what malloc is doing, and basically malloc is gonna be returning a pointer to the first character of this allocated region. Yes. So basically we are gonna be allocating 16 bytes of data, so in the heap, and then we are gonna be moving the return address of the malloc into the register 15, the register 10. I'm sorry. So register 10 will be containing the address of the allocated data. Then we do the same thing. So we are again allocating some other kind or some chunk of data or some piece of data. So we're passing down 16 again to the register 15, and then we are allocating again using the malloc. And then we are moving the result into the register 11. Then what do we have? Then we are putting some kind of message. So what is that message exactly? So we can just check that out. So it's supposed to be this one, which is enter your username and password and continue. So this is just printing e-message or e-welcome message. And then basically you give your username. So this is give username message, and then you read the username. So basically we are gonna be reading 0x13 bytes of data. And then we are going to be moving register 10 as the destination address. So destination address is going to be register 10, which is the first allocated space, which is this one. We have already allocated 16 bytes of data and moved the result to the register 10. Moved actually the address of the first byte to the register 10. And then we will be printing the username. So this is just printing the username using puts. We are now no longer using the printf. We are just getting back to the puts. Then we are give the password message, and then we read the password. So again, basically we are reading 0x13 bytes of data, um, and we are moving the results. So the destination address is going to be register 11. So register 11, yes. And we basically read the password into this region, which is pointed to by the register 11. And then we uh, move that password to testing phase. We basically test the password. So if the result is 0, then uh, we basically gonna be going on to the failed message. Otherwise, we will be just unlocking the door. But obviously, we won't be able to guess the password since we don't know how exactly the process of testing is happening. Yes, and then we are passing down the register 11 um, to the free function. Now this is the interesting part. So the free function, for those who do not know, since we use the malloc to allocate dynamically space in the heap, we use the free to free the data um, from the heap. So basically free is used to just delete, for example, the allocated data that we have allocated from the heap, just for example some other process, let's suppose, want to use that address. So to make this process use that address, we need to free it, for example, to just say, hey, you can use that address, you can use that space, it's okay. So we use free to just free space from memory. So we pass down the register 11 just to free that space of data, and we also pass down register 11 to free it also. And then we just put back the two values and then we return. So just basically as a conclusion, just from reading all of that, what do you think is the way that we can exploit that? Well, if you go and check, for example, we have to check first if there is any unlock function door. So there is an unlock function door. And the other thing to do is, if we go back to the main, we saw that he is calling the login. So if you try to again to just try to change the value of the return um, of the login stack frame. For example, just go to the unlock door as we have did with the buffer overflow videos. um, then we will be cool. We should be solving the challenge and we should be unlocking the door. But how can we do that? Just if we go back to check, for example, the login again, uh, if you go back to the login function, what are the ways that can help us overwrite the return address of this login? We had to find a way, but just to explain more what is happening exactly, we are allocating, for example, in here 16 bytes of data, as you can see. But we are reading actually, what is the part where we are reading? So, but for example, for the username, we are reading 0x13. So there is some margin of overflow. We can overflow something because we have allocated 16 bytes, but we are reading exactly. Let's just open up Python. But we are reading 48 bytes of data. So we have some margin of overflowing something. We had to figure out exactly some entry point that can lead to some kind of exploit. So this is basically the first idea that can came once we read something like that. Another thing is we had to find some kind of function that can, for example, change the value of the return address. So let's, for example, try to do this dynamically just to explore exactly how the attack vector is working. So basically, uh, I'm gonna breakpoint exactly before we read the password, just before we try to check it. So if we continue, so we have to reset that. So yeah, well, I'm gonna be sending item byte, and then I'm gonna be sending item byte 1, 2, 3. We hit the breakpoint. Okay, so what do we have? So this is the heap space. So basically, this is the heap space, and this is the stack space. So if you remember, I have already explained that on the reverse engineering videos that you should check out if you didn't watch those videos. Um, that basically, if you go into the memory, we can just divide them as something like that. This is where the stack is, and this is where the heap is. Uh, just a second, and this is where the heap is. So this is the heap, and this is the stack. I'm sorry for the bad writing. Yeah. So this is the heap and this is the stack. So basically they are divided together, and you can see that also in the memory for example when you look in here. So this is basically where the username is living, and this is basically where the password is living. And as you can see, there is some kind of space between the stack and the heap. So how now this is the really interesting question. How can we go from the heap to the stack? How can I, for example, change a value that is living in the stack? So for example, in this case, this is the return address um, of the stack frame, of the login stack frame. So we have to find a way to change this return address. And the question is, how can I go from the heap space to the stack space? This is the interesting question. So if we can find an answer to that, or we can find a way to answer this question, then we will be solving the challenge. Because once I find a way on how I can change this value from the heap, because basically the input is basically inside of the heap. It's not inside of the stack. If it was inside of the stack, then I can override that value with another value, just as we have did in the other challenges. So this is the interesting part. What is the function now? Once we take a look again at the code, what is the function exactly that can, for example, help us do that? So we try to do that, for example, using brute force. So we don't have control over malloc, since those two malloc functions are just allocating data at the beginning, and they are not taking any kind of input that we will be giving. Um, so the only functions that take our input, for example, to go and check, are basically the test password valid and the two free functions. So here's the idea. So basically, we will be targeting this free function. So the first thing that I thought is I had to understand exactly how this free function is working because I do not know how to how to how do this function works exactly before solving the challenge. And I took some time to do the same approaches I have used when I reverse engineer anything. I tried to exactly understand how this free function is working. So the next step, guys, is to understand how this free function works and try to reverse engineer, for example, the free function that we have, and then try to figure out an exploit. So those are the steps that we will be doing. So the first step is to understand how the free function working, and somehow I landed on this beautiful article that explains exactly how the free function works. So let's read that together. So what do we have? So assuming you are interested in knowing the internal details of free, I would like to explain in one of the ways I implemented it. So um, overall, a free function releases a chunk of dynamically allocated memory from the heap region of the process address space. It takes a void pointer starting address of the chunk to be freed. Before beginning the internal details, let me tell you a little bit about the internal data structure maintained and manipulated by call to malloc, calloc, realloc, and free. So let's keep the performance and other optimizations aside, as the general idea behind any malloc-free implementation will typically remain the same regardless of any sorts of optimizations and or improvements. Okay, that's cool from him. He will be just explaining for us how exactly the free is working. So it is a typical linked list of blocks. Okay, this is interesting. So basically the free implementation is based on a linked list. So for those who do not know what linked lists are, linked lists are basically data structures. So basically, we create a structure in C that has some kind of block. So this is basically just a simple, for example, linked list where you have those blocks. So basically, this is the first block, this is the second block, and this is the third block. And basically, the structure is having some kind of, let's say, standard structure. So basically, this is the next, for example. So this is the next, and this is basically the value that the structure will be holding. And the thing is that the next is a pointer that points to the next block, and the same goes for the second and the same goes for the second block. It will be pointing to the third block, and so on. So this is basically how you create a linked list, and each one of those blocks is having a value inside of it. So this is basically what a linked list is. So it's a block. So a block is a contiguous region of space, usually partitioned into two chunks. So basically, the linked list that we will be having is will be divided into two chunks. So basically, this is a chunk, and the value is a chunk. Yes, so this is what a chunk is. So the first chunk is the metadata chunk. So this is the very first region, which is a fixed size space used just to maintain the information for the data chunk. So in the majority of the implementations, just following information is stored in this space. So what do we have in the metadata chunk? So so we have, first thing is free or allocated. So whether the data chunk is free or allocated. And we also have the size of the data chunk. Okay, interesting. And we have a pointer to the next block or the address of the next block metadata chunk. And we also have, if allocated, store the starting address of the data chunk that was returned when the space was allocated by some prior call to malloc. So basically what the malloc doing, so if we take a look at this diagram, so this is basically how stuff is going to be allocated inside of the heap. So it's in this format, which is a linked list. So we also, for example, we have the first block. So this is the first block, which is the data block one, which is divided into two chunks. The first chunk is the metadata chunk, and the second chunk is the data chunk. And basically the first, for example, data block is gonna be pointing to the second block, and the data block number 2 is gonna be pointing to the next block, and so on. And the thing is that the metadata chunk is basically having informations, or is storing informations about the data block, about the actual data block, and about the previous, and about the let's say not the previous, the next data block. So this is basically what we have, and the data chunk will be actually having the data that we will be storing. So for example, if I'm gonna store my name, for example, ironbyte, inside of this allocated data block, so ironbyte will be in the data chunk, and the metadata chunk will be having informations about where my data is exactly, and what is the next data that we can access, and it will also have the size of this whole data block. So the metadata is used as a way to give informations about the space that we are allocated, the next thing that we can go on. So basically, it's metadata. That's why we call it metadata, because it's some kind of informations. And the data chunk, this is writable by users or client applications. So in other words, address returned by malloc should always point to the data chunk part of the block and not to the metadata chunk, which is obvious. It should be always pointing to the data chunk, because if, for example, it's going to be pointing to the metadata chunk, then for example, if I send ironbyte, ironbyte is going to be overriding the metadata chunk, which is wrong. It should be going on into the data chunk, and the metadata chunk should be always just some kind of information, that the malloc will be generating just ahead. So we also have size and other information referred to as metadata about this chunk is stored in the metadata region chunk. So I suppose now we have an idea about how the structure of stuff is going to be happening when we are, for example, calling malloc or free. So this is the way things is organized inside of the memory, and specifically inside of the heap. So the above diagram shows a linked list of 3 blocks. As mentioned before, each block has 2 regions for storing metadata and data respectively, the latter region being writable by clients of the malloc, alloc, realloc APIs. The second block is highlighted to depict a free block, which is the data chunk. Again, different implementation might have a separate linked list of free blocks. So basically, this is just a way, by the way, of how we can implement for example, malloc and free using this data structure. We will try. That's why we have to just have an idea about this, and then just go back and reverse engineer what we have inside of the challenge, because maybe the challenge is not implementing this structure. Maybe he's implementing another data structure, but for sure he's gonna be using linked list. But the thing, he might be, for example, changing the flows of some kind of stuff. Who knows? Who knows? Literally, who knows? Yes. So the starting address of the data region is what malloc returns, and is then later on passed to the free. So when the user decides to release the memory for the corresponding data chunk. Okay, so when, for example, we want to free some kind of region. Let's suppose I want, for example, to free this one. So we basically gonna be giving the data chunk address, and he has to find a way to just go back a little to the metadata chunk, because when we free something, we need to just take a look at the informations that we have about that data block. Yes. And now that we know a little about the internal data structures, it is easy to guess that free function just takes in the address of the data chunk and marks the block as free by modifying some sort of a flag in the corresponding metadata chunk, followed by some other bookkeeping type of operations, which is adding the newly freed block to an explicit list of free blocks. So now we need just to think about 2 important things. The first thing is, free function receives an address of a previously allocated data chunk, so this is definitely needs to be verified. So the address passed into free function should have been returned by a prior call to malloc, which is true. As we need to make some modifications to the corresponding metadata portion of the block, we somehow need to get the address of metadata chunk. It means the starting address of the entire data block. So it is fairly simple to implement these things. So in the majority of the implementation, size of the metadata region is referenced using a macro. let's name the macro as metadata size. Okay, as so basically this is going to be the metadata size of the chunk, how much data it's going to be taking. So basically, because this is a structure that's going to be holding a lot of attributes, for example, the next thing that we will be pointing to, the size, for example, such a thing like that. For example, this is basically can be just an example of a structure. Yes. So as the address is of void type and is an aligned one, malloc should always return an aligned address. It is safe to cast it just uh, to just a pointer to a character type. So this is basically done just to simplify the pointer arithmetic. So assuming the argument passed to free is a void pointer, we would do, for example, this is the data chunk address, which is just an address to some kind of pointer, just an address, for example, let's suppose in the memory. And then the metadata chunk should be the actual address that we have, which is the data chunk address minus the metadata size, which is pretty just obvious for why. Simply for example, let's suppose there is an address that is pointing to the data chunk. To get back to the metadata chunk beginning, we just have to subtract um, the metadata size from the data chunk, which is pretty obvious, I think. So almost all the implementations will use a struct to represent store the informations in metadata chunk, commonly known as block header. So for example, let's just take a look at this metadata, for example, this metadata chunk where we can also call it block header. So for example, we have a size, we have the next, we have a previous, and we have the start of data region, which is just a character, for example. Where what is exactly just it's just the address of the first character in the data region. So this is, for example, an implementation of how we can implement a metadata chunk, or exactly a metadata structure. Once we can combine them together, we can create, for example, um, this thing. So this is basically going to be a structure, and this is going to be basically allocated using, for example, the malloc. So this is what this thing is doing exactly. So yes, so the first three fields are pretty much self-explanatory, and the last field is very important and useful, as you will see below. So now that we have the address of the metadata chunk, we can just cast it to the block header type, and the block header type could be something like that. For example, the block header multiplied by the data block is equal to the block header. So basically, it's not multiplied. So basically, this is just a pointer on the block header. So we can create a data block, and then we cast it like that. So this is basically how we can, for example, create a block header. So to verify that the address passed to the free was really returned by a prior call to the malloc, we just need to check this one. We have to check if the data block starting region is equal to, basically, just guys, when you create a pointer on something, when you create, for example, this data block variable that is already pointing to this block header type. So basically its type is a pointer that points to the block header. Usually when you want to access the attributes that are in this structure, you usually use this arrow. So the data block start data region should be equal to the data chunk address. So if it is a valid address, then we start working on. Otherwise, we should be just sending invalid addresses to make sure that we are not going to free some kind of address that was not allocated by the malloc, which is a typical way of how we can sanitize always the inputs that was given on by some kind of input. Who knows? Yes. So I suppose now we have an idea about how the structure of these things is working exactly. So let's go back and try now to take a look at the memory and try to figure out exactly if those structures are the same or not. So just by assuming, guys, I will be assuming something. So basically, if we go and check the register 10 and the register 11, which are holding basically some kind of addresses that was returned by the malloc, and since we said that the malloc is going to be returning an address on the data chunk, not the metadata chunk, it's going to be the data chunk. So the register 10 and the register 11 should be holding the addresses of the data chunk of both the regions that were allocated. Okay, if we go now and check them, so register 11 is 240E, so this is 240E, which is this one, and the other one is 2424. So this is 24. So this is 2424. Yes. So before the data chunk, we should be having the metadata chunk. So for example, for the first allocated space, so those are 16 bytes, and before them, so this is the address of the data chunk. So this is basically the allocated space for the data chunk. Before the data chunk, we should be having the metadata. So this is supposed to be the metadata for the first, for example, region that we have allocated. And for the second one, this should be the metadata of the second allocated region. And this should be the data chunk. Now, this is really interesting. And just by using this analogy, we can just also conclude that this is also some kind of metadata of another region. And this is basically the allocated, let's say, the allocated data chunk of that metadata region. So that means, guys, that once we look at this beautiful layout of a heap, and we can just conclude a lot just by reading this article and understanding exactly that there is some kind of data chunk, there's some kind of metadata chunk, then okay, so yes, so this is the metadata chunk of the first one, and this is the data chunk that we have sent to the input. And the interesting thing, since we saw that we are allocating 16 bytes, so this is basically supposed to be the space of the data chunk of the first allocated space returned by the malloc, and we are reading basically 48 bytes, so we can override the metadata um of the other um of the other spaces too, or of the second allocated space. Now here's the thing. Now just by looking at that, we know exactly that we have a metadata. We don't know exactly. This might be also, who knows? This might be also included in the metadata of the first one. So just to make sure now that I have understood everything right, we have only one step. We need to only do one more step, which is reverse engineer back this process to understand what are those values exactly before the data chunk, to just, let's say, reverse engineer back the structure to get, for example, the structure of the metadata and how exactly the process of freeing is working. And once we do that, we are now completely ready to go and exploit. This is basically how we approach this problem. So yes, so it's time to go in, just reverse back the free. I think I have did that work um, from my side, and I'm gonna be explaining to you what I did exactly. So this is the free function. I'm gonna be zooming a little. So this is the free. So the free basically is gonna be taking basically the address of the allocated space returned to by the malloc, and that address is specifically the address of the data chunk. Now, here's the interesting part. Since we know that um, since we know that the address allocated by the malloc is pointing to the address of the data chunk, to go back to the metadata, since when we are going to be freeing something, or we are going to free exactly some kind of space in the memory, we need to take a look at the metadata. So the first thing that he's gonna be doing is he's gonna be saving the register 11, which is a pretty common way that we do whenever we call any kind of function. We save the registers that we will be using. Who knows? He might be using, or he might not be using. Anyway, we save the register 11. This is the first step. The second step that we are going to be doing is we are going to be adding to the register 11 minus 6. So we are basically going to be subtracting 6 from the register 11. Now I'm going to be just adding here a little comment that register 11 is having the address of the data chunk. So I'm going to be assuming, guys, that we will be freeing, for example, let's suppose this first address, which is this one. So I'm gonna be just jumping to this call. So if you jump to this call, so basically the free is going to be passed on this address, which is the register 11. So for example, 2424. So basically, I'm gonna be trying to free this chunk of data, which is this one. So to do that, so we basically just push now the register 11. So I'm sorry, register 15 should be equal to the address of the data chunk, which we have talked about, which is this one. And then he is going to be subtracting 6 from the register 15. So just by subtracting 6, that means that he will be now having access to the metadata. So the metadata size can be concluded as 6 bytes. This is just by trying to interrupt this instruction in assembly. Now, next thing that he will be doing, he will be moving to the register 13 the address pointed to the new address. Now, just by assuming that, now this is basically the address of the metadata. Now, the register 15 is going to be having the address of the metadata. So if we do that, now he will be accessing the register 15 plus 4. So this is the base address, which is register 15, which is containing the address of the metadata plus 4. And then um, and then he will be ending that value which we have access. So we need to know what this kind of attribute. So he's actually now trying to access some attribute inside of this structure. So basically he will be trying to access some kind of attribute inside of this structure. So by adding 4 to the base address, he's accessing some kind of structure. So this is basically the way we implement structures. I don't know if you have saw that when you try to reverse engineer any 8664 binary, but to access any kind of structure, we usually use the base address plus how much offset it is inside of that structure. Yes. So register 13 now will be we will be ending the register 13 with this value, and then um, we will be moving that result to the register 15 plus 4, which is this one. So the metadata plus 4, which is the same place. So basically what we did was we loaded that attribute inside of the register 13, and then we ended that value or that attribute specifically in that structure, which is the metadata one, um, with this value, which is 0xFFFE. Now, this value has a really interesting thing. So after I reversed the code, just to give you the intuition behind this value. So this value is going to be used to, for example, just mark, for example, let's say I want to mark a block as allocated or not allocated. How do we do that? So to do that, he basically created a variable, or let's say an attribute inside of the metadata structure that is either going to be 1 or 0, which means that, for example, for example, if I have, let's suppose, if I have a 0, 0, that means it is released, let's say free, and if I have a 1, that means that it is allocated. So this is basically what he's doing. And basically what he's doing here is he's checking the lowest bit inside of this register 13. So for example, if register 13, let's say, is having 111 0, then the result just ending that with that value would give you 0, obviously, because the FFE is uh, the FFE is basically having the bit 0 at the end, because E is basically 1110, so the lowest bit is going to be 0 and the other ones are going to be 1. So only thing that he is going to be checking by using this and is that he will be checking if the lowest bit or or the LSB more specifically, which is the least significant bit, inside of the register 13 is equals to 0 or not. But he's not going to be checking anything. He's basically just setting that register 13 bit to 0. Just by using that, he's setting that to 0. So he's setting the lowest, the LSB of register 13 to 0. And by just calling register 13, we mean that the register 13 is going to be just storing an attribute of the metadata structure. I hope you just understand what I'm talking about. Anyway, and then he's moving the new value to the same attribute, which means that he just set the LSB of that attribute to 0, and then he loaded back that value back. Anyway, we then move what's in the register 15, which is the first attribute. Now we are accessing the metadata directly, which means that we are accessing the first attribute inside of the metadata, and we are moving that value inside of the register 14, and then we are accessing um, so I'm gonna be calling that, for example, I'm gonna be calling that second address of the second attribute. Well, let's say I'm gonna be calling that second attribute, just to make sense of that. I'm gonna be calling that, for example, third attribute, just to make you understand exactly what is happening. So if we call that second attribute, so we can just call that ATR, just a short name. Anyway, so we are now accessing the second attribute plus 0x4. We are moving that value to the register 12. Now this format looks the same as this one, and since the register 15 was pointing to some kind of metadata, then I suppose the register 14 now is supposed to also point to some kind of metadata. So that means the register the register 15 is having some kind of pointer at the beginning of its structure, which means that the metadata is having some kind of other metadata pointing to, which is a typical way on how we can implement linked list. So that means that the metadata chunk is having an attribute that points to another metadata chunk. So the second attribute, or this first attribute, I'm sorry, is going to be basically another metadata. So this, let's suppose that we will be calling that, for example, previous, just to make sure that we have understood what this thing is. So this is basically a previous. Yeah. So this is the attribute that we will be pointing to, and it's actually also another metadata. So we can just call it, for example, like that. So meaningful names are really important when I reverse engineer, guys, because I need to make sense of what this code is doing. So basically, I try to do as much as I can of a good naming to make sure that I reverse engineer the code and get a decompiled version. So the previous of that is going to be metadata. So this is the previous metadata. Yeah. So now I'm going to be accessing that previous metadata. I'm going to be accessing that previous metadata plus 4. So basically I'm getting another metadata, and I'm accessing that structure again. So I'm accessing the same attribute also, which is 0x4, the same as this one. So that should be having a meaning. That attribute should be having a meaning. Yet we don't know yet what this is exactly, but we will explore it more. So then he is so this is basically going to be the third attribute, third ATR. So this third ATR is going to be so this third ATR is going to be ORed with the 1, which means that he will be ORing that with the 1, which means that it's the same thing as saying, if I'm going to be checking, so checking if the lowest bit again, lowest bit, or the LSB of the third attribute um, is equal to 1. So if the third attribute is equal to 1, so what do we do? So if the third attribute is different to 0, which means that G and Z, which is jump if not 0 to this address. So this address is supposed to be this one, which is this one. Yeah. So we will be checking if the third attribute is different to 0, then we go and jump there. Okay. So we use the previous metadata, by the way, in here, and we have accessed again the third attribute that we don't know exactly what it is. So let me just point that out. Just after doing some reverse engineering also with this customized data, it just came out that this offset exactly 0x4 from the data structure that he is having is supposed to be the size. It's supposed to be the size um, of the whole data chunk. So basically, to know what is exactly the size of this data chunk, we have created an attribute inside of the metadata that we will be storing the size. And at the same time, to know if this data chunk is allocated or not, we have just pointed to the LSB as the one that will be saying if this data chunk is allocated or not, which means that the third attribute, which is the size, is going to be saving. So basically the size of the data chunk plus y. So where xxx is the size of the data chunk and y is a flag that we will be using to check if the data chunk is allocated or not. So that means to check if the data chunk is allocated or not, we have to go to the size and we have to extract this bit or this latest bit or this byte exactly, or just let's say the LSB of this byte, and check if that value is 0 or not. If it is a 0, that means that it is released, and if it is a 1, that means that it is allocated. So this is exactly how these things work. So this is why he keeps on ending that one. So what he did actually in the first stage now, for now, just to understand that, just to link that. So we can, for example, now just try to rename things in here, and third attribute is can be called size. So he is having, or now the size is should be equal to the size and the 0xFFFE. Now just to make sure that we have understood everything right, so the size when we ended with that value, we actually get the flag. So we are setting the flag or the LSB of that register 1320, which means we are setting the flag of that metadata, or of that, let's say, of that data chunk to 0, which means that we are releasing actually the data chunk that we have passed on. Don't forget that, guys, we have passed to the free an address to a data chunk, and it seems out to be that this data chunk is pointing to a previous data chunk. So I think we have some kind of options that we will be exploring, because for example, when I want, for example, to delete this one, or let's say not delete it, I wanted to free this data block, but it is actually linked to another data block, and it also might be also linked to another block, which is, let's suppose, next block. So I'm supposed to link the previous with the next and then free this data block. So there is some kind of options to explore. So we're going to be exploring those options together as just after reverse engineering the whole code. So basically now we came to the conclusion that the the offset for from the address or from the base address is going to be pointing to the attribute of size, which is the size of the data chunk. Now, once we have finished that, we should be going back and trying to make sure that we change everything inside of the of the code that we have. So this is going to be the size. So this is the size, and this is the size, and this is the size. Yeah. So basically we are checking if the LSB of the third attribute. So we are basically if the flag is equal to 1. So if the flag is equal to 1, that means that the previous data chunk or the previous metadata or the previous block is allocated. Otherwise, we will be jumping to another block. So basically, the first thing we did was we set the actual flag for the data chunk that we have passed to the free as free, which means that we just set it to 0 just to say that we have released its data chunk. And the next thing that we have to do is we have to go and check the previous metadata, and we will be doing some kind of other checks. So what we did also, so if it is not released, for example, so if this size of the previous metadata, and we actually check, so if the flag, let's just make sure that this is the flag, so equals to flag. So if the flag of the previous metadata is different to 0, that means that it is not released, that we jump to this address. Otherwise, if it is released, then we go to this block. So it means that if the previous block is already free, then we will be doing some kind of stuff. Okay, so what do we do first? First we move 6 to the register 12, so register 12 plus 6, and then we add the register 13, and register 13 is supposed to be saving the size of the actual metadata that we have. So it's actually the size of the address that it's actually the size of the data chunk that we have passed to the free to be freed. So basically this is going to be holding 6 plus so it's going to be 6 plus size of the actual data chunk to free. Yes. Yeah, so this is just a simply new size, and then once we do that, we go to the register 14 plus 0x4, which is the address of the address of the previous data. So we go to the address of the previous metadata plus 4, and we just set it to register 12, which is the new size. This is basically a new size, which is 6. 6 is supposed to be the size of the metadata chunk that we have freed, which is this one. Since we have freed this, we set the flag as 0, which means that this block is free. It's over. So what we will be doing is um, once for example we just freed this data block, and the previous one is not is also freed, then what we will be doing is we will be taking the size of this metadata chunk and the data chunk, which means that we will be getting the size of the whole data block, and we will be adding that to the size of this metadata chunk size, which means that we are going to be linking them together and just regrouping them together, so that this data block will be added to this data block as size, which means that we will be getting all this space as a contiguous space. This is what's really happening. Okay, once we do that, so the previous metadata plus 0x4 is equals to the new size, which means that the size of the previous is going to be the new size, which is the size of the actual, I'm gonna be calling that actual, which is the one that is in the center. Size of actual plus 0x6. So it's going to be the size of this data chunk plus the 6 of the metadata chunk of the one that is in the center. So once we do that, we go and we actually access the previous metadata plus 0x2, which is now a new offset. So we basically access that using, we try to access that directly, and we try to access that using the 0x4, and then we are using another offset which is 2. And after reverse engineering that code my whole the previous days, actually came out that this 0x2 is actually an address pointing to the next metadata, which means that the structure now is having a previous and a next and a size. Those are the attributes of the metadata chunk structure. Yes, so that means that the previous metadata plus 0x2, which is now, it's like I'm saying that the previous next is going to be, um, the register for 15 is pointing to the actual, so it's going to be the actual uh, next, since 2 is the next, since once we try to use the offset 0x2 from that one, we actually just access the next metadata. Gonna be just calling that metadata. And this one is metadata 2. And this one is obviously the actual metadata that we are trying to free. This is the metadata. You see, there is a lot of there is a lot of trouble when you are trying to reverse engineer this code statically, especially from a function that we have used a lot in our lives. Yes. What do we also have? So register 13 now. I'm gonna be saving that next inside of the register 13. So it's actual dash previous. I'm gonna be just dash next. Next. So I'm gonna be using um, just using without using the metadata, just for you to understand that actual is going to be the actual metadata and the next is going to be the next metadata, just as abbreviations for you to understand with me what's happening. So yes, and then I'm accessing that register 13, which means that I'm doing now actual next, uh, next and previous, since at the address at the offset 0 we have the previous, so we are accessing the actual address next, which means this one. I'm going to be setting the next, uh, the actual next of this one as, and yes. So what is happening is I'm going to be accessing the next, which is this one, and the previous of this next is going to be equal to register 14, which is the actual previous, which is the previous actually, which is this one. So I'm going to be linking this one with this one. This is the way we are doing the free. So to free that, I'm going to be linking this one with this one. Okay, this is interesting. And then I'm going to be setting the actual previous, since we are accessing that register 15, and register for 15 is holding the address of the actual one, which is the one in the center. And when accessing the first attribute, so it's the same as saying, actually it is the same as saying like that, 0x0 register 15. So it's the same actually. So when you do this, you actually do the same thing as this, which is the way we actually access the previous. Yes, so the actual previous is going to be passed to the register 15, which means that the actual now is going to be the actual previous. Okay. So what do we have next? Once we do that, we go back and uh, we move into the register 15 or 14. I'm sorry, the previous is going to be the actual, uh, which is the actual previous. Okay, so the previous is going to be the actual next, I'm sorry. So the previous is going to be the actual next, is going to be the next of the actual. and the register 13 will be holding the register 13 will be holding and basically this is register 14. It's getting hard actually. um okay, and the register 13 is equal to the register 14 um plus exactly, it's not a plus, it's accessing the size. So we are accessing the size, which is register 14 with, by adding a 4 we are accessing the size. Yes. So register 13 will be equal to the size of what exactly? So register 14. So yes, since the register 14 is pointing to the next, then this is going to be the size of the next one. And what we do, we actually again try to see, we try to get the flag. So register 13 equals to the flag of the next. And again, we check if the next flag is 0 or not. To just check if this one is allocated to someone or not, or if it is released. Then if it is released, then everything is cool. We go to do this block, otherwise we just jump in here. So if it is free, or if it is released and no one is using that, then we can just add that to the block. So what we do register 13 equals to the size of the actual, and the register 13 equals to the size of the actual, which is the one that we have, plus 6. Plus 6, yeah. So basically what we do, we just set the size of this one as the size of the one that we will be releasing. Yes. So we just simply add that one. We just keep on adding that one. And once we do that, we move the result to the size of the register 15. So now the size of the actual is going to be equal to the size of the actual plus 6. Once we do that, we just link the actual next. We link the actual next is going to be the previous next. So the actual next will be the previous next. And once we do that, the last thing that we have to make sure of is to check out the register 14, which is the previous. Now wait a second. It's not the previous. Wait a second. It's actually the next. Yeah, since the register 14 is basically saving the next, since we are now in the other case. Oh my goodness, it is a lot of code and a lot of options. Okay, the previous now, the next previous, since we are doing that with a 0, so we are accessing the previous of the next. So the previous of the next should be the actual one that we have. I suppose we didn't change the register 15 since the starting of this code, so it should be also pointing to the data chunk, which is the actual one, the one that is in the center. So yes, once we do that, we have finished now reversing the code. So what are the options that we have? Now we have a lot of options. Now before we do the options, I'm gonna try to reverse all this code back and decompile it, just to a C code that you can understand more what is happening. So what is happening exactly? Just after doing a lot So just after doing a lot of reverse engineering, so I reversed back the metadata chunk. So this is the metadata chunk. So this is what the metadata is going to be pointing to. So this is the metadata, and we have a structure. We have a struct that is in the meta that is pointing to the previous metadata. And we have also another metadata that is pointing to the next. and we also have a size. So a size basically is a 16-byte value, so we can just set it to a 16-bit value, so it should be just a short. So short basically has a size of 2, and this should be having a size of 2, and this should be having a size of 2. Don't forget guys that we are basically working on a 16-bit architecture, so all the values, all the pointers will be having a size of a 16-bit value, which means that they are 2 byte size. So this is a 2 byte, this is a 2 byte, this is a 2 byte, so this is 6 byte. So the size of the metadata is 6 byte, and this is why, for example, this is why we have the data chunk. To get back to the metadata, we have subtracted 6 from that one. That makes sense. Now if we go and try to reverse engineer more stuff, now I'm gonna be defining a macro. I'm gonna be defining a macro as the article said, and I'm gonna be setting the meta size as the size of the metadata, which is, in our case, it's gonna be 0x6. And we can check that, by the way. We can check that just by running a simple command. But well, we cannot run that on my computer because my computer is a 64-bit architecture. So basically, I cannot do that. So because the pointers are might be 8 bytes of size, and we have to just make sure that you want to check the metadata size. You can just check that, for example, on an MSP 430 card. Yeah. So what do we have now? We go to the void. So I'm gonna be pointing to, so I'm gonna be trying to reverse the free function. I'm gonna be trying to write this customized one that he has in front of us. So basically it's gonna be taking a void address, and that void address. So what do we do? So the first thing we do is we get back, so we get the metadata chunk address. So the metadata chunk address, so we have the address. So the address should be, so I'll be casting that to a pointer that points to the metadata. So since we are passing a void, since we are passing a pointer that points to the void, to nothing actually, we can just align that now with a pointer that points to a character. So the address that we have minus the meta size. And by doing that, we actually get the metadata chunk address. Yes. Now the thing that we have to make sure, so this code has set the flag, set the flag of that data chunk to 0. So to get exactly the flag, we have to use the size. So the size is going to be access. So we need to access the size, and then we need to do uh, address size, for example. Wait a second, we don't need that. Okay, so I'm gonna be ending that one. I'm gonna be ending that one. I'm gonna be ending that with actually the 0xFFE, which is this value. Just to turn, this will be turning or setting the flag to 0, which means that it's going to be freed, so it's released. So basically by doing that we are releasing that that chunk of data. And once we have finished that, we need now to check. Now we need to check the different options that we have. Now what are the different options that we have to check? So those are the different options. So if I'm going to be freeing this, I need to check if this one is free or not. So we basically have exactly 2 by 2 to the power of 2, which are 4 possibilities to check, which is 0 1 0 0 1 0 and 1 1. So if they are 2 free or not, we have to check all those options. So we can, for example, set all the options, write all the options here. in here, for example, we have four options to check. First one is, for example, when the previous and the next are not released. Not released, which means, for example, they are not released. For example, are free. And the second one is, for example, when yes, and one thing to say in here, for example, when the previous and the next are free, we have to do something. So we have to, for example, we have to, let's say, allocate just, let's say, when the previous and the next are free, which means um, they are free till, well, this is a pretty obvious thing. Let me just think a little. What has happened when the previous and the next are free? Well, we have well, let's just start with not the previous and the next are free. Let's say we have the previous and the next are not free. For example, when they are not free, which means that we have just simply to go and just free this one and let those two or and let these two as the same as they are, which means they should be just we should be just setting the flag to 0 to just say that they are the chunk that we are doing is free, and that's it. For example, the second one, for example, we have the previous and the next. Um, for example, the previous is equal to 1, which means that it is, let's say it is equal to 0, it is released, and the next is equal to 1, which means it's not released. What has happened when this happens? What So we have, first thing to do is um so the flag of the actual one should be the flag of the actual should be equal to 0, obviously. um and the total size um should be added, so the total size should be added to the size of the previous. And what else do we have? So the next of the previous should the next of the previous should be updated, so is updated um, to be the next, yeah, to be the next. And the previous of the what is next? So the previous of the next should be updated to be also the previous. Yes. So what is now, I think, the third option? So the third option should be the previous should be, let's suppose, um, now let's suppose both of them are free. So it's going to be the same as the one. So same as the option 2. For example, when both of them are released, it's going to be the same as the option 2, and the total size of the next should be added to the previous, I think. What else? So we have to update the next of the previous also. Uh, we have to update the next of the previous to be the next of the next. Yeah, and we also have to update update the previous the previous of the next to be the previous. And we can just conclude, well, we can, I don't know, for example, conclude that this is going to be the union of these three chunks. Anyway, Once we do that, we have also to just check one more option, which is previous is equal to 1, and next is equal to 0. So this is going to be the latest option. So as always, the flag of the actual should be equal to 0. What else? Well, so the total size again of the previous, or now it's not of the previous, so of the next now should be equal to, or should be appended to the size, yeah. And then the next should be updating the to be the next of the next, and the previous of the next should be um should be what exactly? Let me think. You see, there is a lot of options. It's basically just, wait a second. Should be staying the current. Stay should stay the current as the current address. Yeah. So those are all the different options that we can create just by doing all of that. Now let's go back to the free and try to implement them together. So what do we have? So the first thing that we have to do is we have to check if the previous is released or not. So if the previous is equal to 0 or not. Uh, let's say previous flag is better, is more significant. So if the previous, so if the address of the previous, so the if the previous address, and we get to the size and we end it with a 1, is actually different to 1, which means it is not released. Um, yes, it's released, I'm sorry, which means that the previous flag is released. So the address previous size should be equal to the metadata, so this one. So we have to add 6, and we have to add the actual data that we have. So basically we add the meta size, we actually add the meta size, this one, plus the address size of the actual one that we have, which is this one. So basically we added the 6 and we added the size of the actual one that we have. Once we do that, well, let me just do a little bit like that. Let's make it cool. Go that. Okay. So next, what do we have to do? We have to take um, now since we have understood the logic, I don't have to take pretty much a look at what is happening, since now we understood that we have those options that we have to implement. We basically try to implement that. So basically what's happening now, if the previous is released, then the address of the previous, now the size of this data block should be equal to this one plus the actual size that we have. And the next thing that we have to check is that the previous next should be equal to the address of the next, exactly. And the address of the next of the previous should be equals to the address previous, exactly. Yeah, and also the actual address now that we have should be equals to the address of the previous. Okay, so this is basically what should be happening. So, but if we have, what if we have to check, we have also to check if the next flag is released. So if it is released, yeah, so we have to take the size. So so the address size, so nope, it's not going to be like that. So the address size should be equal to the we should be adding plus equal, so we'd be adding the address size, so, or the address next size plus the metadata size plus adding the metadata chunk size. Okay. And then we do the address next. We obviously have to add the next to the address next. So the next is going to be the next of the next. And then the address next should be the previous address. And once we do that, we have completely just we have just to return now at the end, since we have already released that in the first time. We have released the flag and we have checked the different cases that we will be having. Yes, that's interesting. It's actually took me 2 days to reverse the code basically and get this code in front of you. As you can see, we already take, I think, 1 hour or something just to reverse the code. So basically this is the free now. I think we have a clear idea about what is happening exactly inside of this free. Now, how can we exploit this free functions? Now, this is the question. So let's go back to the Sublime text. Let me go back to the microcorruption, and now let's take a look at this thing. So now the interesting part is to understand exactly the layout, since we have reversed since we have already reversed the code. Yes, so let me just take that one. Let me just drop it into Sublime. Just get it at the end. So yeah, this is a E2 in here. So what do we have? So this is basically the dump of the heap before we start, or just before we start freeing anything. So basically, since we said that the metadata size is 6, so this is actually the metadata. So those are 6 bytes. And then we get to the data chunk. So this is the data chunk. And this is actually the metadata of the second block of data. And this is the data chunk of the second block of data. And this is another metadata chunk, I suppose. Um, what else? What else? We also have this data block, or this data chunk of data also. Now we need to dereference those values, since if we take a look now at the structure of the metadata, we see that the first one is going to be the previous and the other one is going to be the next, and this is the size. So this is going to be the previous, this is going to be the address of the next, and this is going to be the size. But all of them are a little Indian, which means that the bytes are flipped. So this should be 2408. So if you go and check that inside of the code, so if we see like 2408, so 2408 is the actual one that we have. So the previous of this, if this block of data is actually the same block of data, and the next block of data that is pointing to is 24.1e. So 24.1e is this offset exactly. So this 2410, this 24.1e. So it is pointing to this block of data. And then we have the size. So the size is 0021. And the thing is that 000x0021 is actually means one thing. So for example, if you try to end it with a 1, so if you try to end it with a 1 to know if this block of data is released or not, it's obviously allocated, so it should be a 1. So yes, so it is a 1. So that means that this value in here is going to be the size with the flag, and the flag is 1, so that means that it is allocated. Now the same thing goes for the second one. So this is the previous, and the previous of this block of data, which is the second one, is 2408, which is this one, which is starting from this one. I'm sorry. Yeah, starting from this one. Yeah, which is 2408. And the next is going to be 2434, which is this one. So this is another block of data, and the size is the same, and the flag is set 1, and this is the data chunk, and this is now the metadata of the block 3. So the previous is as 24 at 24 1e, which is this one, and the next is going to be 2408, which is this one, and the size is going to be 9C 1F, which is one, which is, if we flip them together, 1F 9C. Now the thing is that 1F 9C, if we try to end it with a 1, is going to be giving you 0, which means that the third block of data, or the third block, is not allocated in the heap, which means because actually the flag is equal to 0, and the size is quite big because we have one F9, so the size of this block of data is big because it's not allocated, that's why. Now here's the thing, we can override the metadata. Now the vulnerability in here is to find a way on how we can overflow the heap. This is the vulnerability we have. Since we have now reverse engineered the free, know what the metadata attributes are exactly, we can now start exploiting, guys. Finally we can now start exploiting. Now we have to try to find a way on how we can override some kind of values inside of the metadata to make it, for example, um, forward that or change some value. So here's the thing, guys. What is the attribute that can be changed? They can be. What is the attribute in this data structure that can be changed when we change something? If you can just take a look in here, you see that the variable that we have changed a lot is the size. And the size can be changed just using other addresses sizes, which means that each time I try to freeze something, I basically take the size of the block that I want to free and add that size to either to the previous or the next, depends on the situation. So the thing is, now we can, for example, set the previous, here's the idea, we can set the previous of the second block to the address. For example, let's suppose I'm gonna be creating a fake chunk inside of this stack. Here's the idea, I'm going to be creating a fake chunk of data, or a fake allocated data. So if I'm going to create this fake chunk of data, so it needs to be having a metadata and it needs to be having a data chunk, right? So it needs to be having a metadata chunk and it needs to be having a data chunk. So I'm going to be supposing that this is going to be the data chunk of the fourth block that I'm going to create, or I'm going to be assuming that I have, and the metadata of that fake chunk is going to be those bytes. So basically this is the previous byte, so this is basically the previous metadata, this is the next metadata, and this is the size of that data chunk, which is gonna be here. And as you can see, the size is coinciding with the return address of the login. What if we can change that value to the address of the allocator? And by doing that, basically, guys, since we saw that when for example I want to free this chunk of data, it's going to be checking the previous, and it's going to be checking if the previous is released or not. So um, by doing that, so since it will be trying to check if the previous is released or not. So for example, if the previous is released, then it will be adding the size of this one, which is this data chunk, this data chunk, and the size of the metadata size of this block to the size of the previous one. So for example, if I set the previous one as the address, for example, of this fake data chunk that I will be assuming that exists, it will be checking if it is released or not first. So, and the size of that data chunk will be coinciding with the return address, and the return address is actually 0x4440. And if we end that with 0x1, we see that it is 0, which means that somehow this return address is also pointing to, now let's supposing this return address is going to be the actual size despite what is happening exactly. So this size is going to be having a flag equals to 0, and that means that he will be assuming that this chunk of data is also released. So that means he will be trying to add the size of this data chunk to this one, and by adding so we will be changing the value of the return address. So this is basically the idea of how we can do that. So basically now if we try to give him the address of the metadata chunk, which is this one, which is actually the offset of this address minus the offset, yes, of this one minus 6, just to get, or I'm sorry, not minus 6, it's going to be minus 4 to get to the beginning of the metadata chunk. So I'm going to be assuming that this is going to be the fake metadata chunk, and the size is this one, and the size, we should thank them because they give us all they already give us somehow an address that is already referring to a flag that is 0, and that means that it is released. And once we trigger the free, for example on this one, once for example we change this, for example we have to change the previous of this chunk to become the address of the metadata of this fake chunk, and we can for example let the rest, for example the next is the same and the size of this one is the same. And yes, so we have to check that out. So we need to know how much data we need to write that, because he will be writing the size of this chunk of data to this one. So basically if we let it 21, it's not enough, so we need also to override the size of this data chunk to make it another one, for example, so that when he can add that value to the size of this one, we get exactly to the unlock door. So the idea is to basically, for example, what is the unlock door address? So the unlock door address is 0x, so it is 0x 4564. So how much data do we need to get from how much data do we need to add to 0x 4440 to get to this one? And just assuming also guys that he will be also always adding 6 to that size, so we need to subtract 6 from that too. So we subtract the 6 too. We hexify that. So basically we have to set the size of this data chunk to 0x11e, so that when he goes to check the previous, he will find out that it was released, and when he will be adding the size of the chunk that we want to free, he will be adding the size of, which is 0x11e, to the actual size of the fake one that we will be forwarding to, which is now, so basically he will be doing like that. So he will be adding 40 plus 0x11e. So this is basically what happened when he will be checking the previous, and if we hexify that we get 45. Wait a second, I think, is that right? Yes, this is going to be 45.5e, but assuming that he will be also adding a 6, which is plus 6, which is the one that he will be adding automatically, which is the size of the metadata chunk of the one that we want to free, which will be giving us 4564, which is the address of the unlock function. Now, so if we just override this address and set it to this address, so that means that we will be assuming that we are now in a new chunk, or just a simple chunk that we have created, which is a fake one, which we can override that value using the username, and we let the next as the same one. We don't actually need it. We also have to change the size of the actual one to 0x11e, so that when he checks the previous, he adds the value that we want exactly to make this size exactly change to, which is the return address. And then there's a little problem in here. We said that the next also intervene. and we are basically in the we are basically in this option, which is when the previous is 0 and the next is 0. He basically also union the through do union of the three chunks. He will be also adding the size of the next to the previous one. What I mean is, by we are in the case when this is released and this is released, we free that and we basically get the size of this data block, get the size of this data block, and we basically add those sizes to the size of this data block. And then in our case, basically the return address is in this data block. And basically by adding these two, we won't be going to the address that we want it exactly, because the sum will be exceeding the exact address that we want to jump to, or that we want to return to. So we have also to change this value, for example, to just set it, for example, to 1. For example, it's not released, so that he won't be using the size of the next. So if we do that, so basically we get, now here's the idea. So the payload is going to be like that. So we will be trying to overflow the username first. So to overflow the username, I will be sending 16 bytes of data, and then I'm going to be so this is the username. So I'm going to be sending 16 bytes of data. Then I'm going to be overwriting the previous chunk that we will be the previous chunk of the second data block. So I'm going to be setting that one to the address of um, exactly that of the malicious chunk or the fake chunk that we have created, or that we will be assuming that is created, which is this one. The address is exactly 439. Okay, let me count. She's 96. Yeah. So we have to flip the order of the bytes. So it's going to be 96 43 plus. Now the second one is going to be the same, so I'm going to be using the same one, which is 24. The next I'm not going to be changing that next. And then we have to change the size of the second block to become 11e that we have set, which should be 0 1 or 1e 0 1, since we have to flip them. Yeah, so this is basically the username. So this is the username that we will be using to override the second block of data. What's next? We have now to use the password. For example, to use the password to override this size of value, the size of the third block, because the third block is already released. And once we free, for example, the second block, it will intervene in the process and add also its size to the return address, which we won't do that, which is the thing that we won't need to have. Yes, so the password should be also, so 41 multiplied by 16 plus um, basically 1. So what do we have? We don't have to change these values. I'm going to be changing only the value that is I'm going to be changing just this value. So I'm going to be setting that to 1, which means that I'm going to be setting the size of the third block as 1. And at the same time, when he will be checking the flag of the third block, he will find that it is a 1, which means that it's not released, so he won't be using that block, and he won't add the size of that block to the return address or to the fake chunk that we have created, or that we are trying to change. So this is basically the address of the block data that I will be assuming that I'm going to be freeing. This is the next of the next block that we will be using to free, and this is the modified modified size that we will need to add to the previous one in order to get to this address, which is the return of the login function. This is a really like consuming challenge. Like literally, there is a lot of details inside of it. Um, so yeah, if we try this one, so this is the username. So now it's the time for truth, I think. Oh nope, reset again. Didn't check the hex one. See, get the password. The password should be this one. Oh wait a second. Let's tab 2. Yeah. So if we check that, what do we have? Yes, and the door is unlocked. Before just unlocking the door, I'm gonna be trying to set a breakpoint to check if the value has changed or not before returning. Reset quickly. Let's do that. Username. Can I reset? Oh, we cannot. Okay, let me just start that again. So I'm gonna be now sending the password. Just this one. Let me just set a breakpoint again. Is this the one? Yeah. Yeah, we set the return. So this is the heap. We have overflowed that, guys. As you can see, um, this is the return address. Wait a second. Yeah. So this is the return address. This is the 1E01. What else do we have? Yeah. So if we now go and check the stack, as you can see, we have now the stack in our, which is this one. We have changed that value. Anyway, if we solve that, I hope you learned something new just out of that, because we did a lot of reverse engineering basically to get this point. To basically do that, we got to understand that the malloc is doing a lot of linked list stuff behind the scenes, and this guy actually, hats off, he explained that very well in his little article. Yes, so we have now one more challenge to go, just a really quick one, which is this string format vulnerability challenge. So basically, if you run that, he will be setting, hey, could you give me a username? And basically, you just give your username. So if you have watched the video of the format string vulnerability, you could just have take a look at that, and basically just to check this code, um, if you go and check the main, basically there's a lot of printf. So basically the vulnerability is the same. He's going to be copying the username into the stack, doing the same stuff, doing the conditional unlock door. But the only difference between that, between the previous challenge Addis Ababa and this one, is that in this one we do not have an unlock function door called directly. Basically, the thing is, in the previous challenge we saw that there is some value that is in the stack that we can override, that we can use the format string vulnerability to override, but this time there is no value on the stack that he will be checking on. So basically he's checking the result by using the register 15, since the conditional unlock door is going to be using the hardware security module, I think 2 or 1 or something. So I think it is 2, because he's using a register 15 as a way to store the result. So yes, so we gotta find another way. So the vulnerability here is the same, since he will be using the username and passing the username directly to the printf, which is vulnerable to the format string vulnerability. So the same idea as the Addis Ababa, we have to figure out exactly an address that we can override, then use the jumps using percentage %x to jump to specific places in the stack, and then we get to write that just using a percentage %n. But the thing is that there is no address in the stack that we want to, that we cannot, that we can, for example, override to get to the unlock door function. And basically he's not even calling that unlock door function for us. So how can we do that? um, there is no unlock door function in this challenge. basically. There is only conditional unlock door. So the way to do that is simply to go and check before the interrupt is called. There is 0x7e. If we change that, for example, 0x7f, as we did in the, as we, as a way to do, that, we have did that a lot in a lot of challenges. We can just simply open up that door. So the idea here is to go and check exactly where this 0x70, which is this one, and try to change it to 0x7f. So to do that, we have exactly to write 0x7f bytes to the output of the screen, and then just forward that amounts of data just to the address that is in here, where exactly the 7E00 is. And once we do that, once he called the conditional unlock door, he will find 0x7f, and no matter what password we give or no matter what username we give, he will always unlock the door for us. So the idea is to go and figure out the address. So we need to go and figure out exactly where this um, 0x7f is exactly. So 7f00, we have to reset that, and then go search for the 7E00. So 7E00 is at this address, which is 44C0. So those are 0, 1, 2, 3, 4, 5, 6, 7, and 8. So it is at 44C8. So we have to go to this address, which is 44C8, plus. Now how much data do we need to write? So we have to write, so the payload is going to be um, um, wait a second. So it's going to be this character plus, we have to add the b in here. 41, we multiply it by how much data. So basically we need to write 0x7f data to the output. 7f minus actually 2 bytes, since we are already writing 2 bytes, which are the address of the one that we want to change. Oh my goodness. No. Okay. Let me just try that again. Payload. Okay. Payload equals to exactly the 24C8 plus 41B, a byte of which is, let's say, 41 multiplied by 0x7f minus 0x2 plus. So basically now we have the subtracted 2, and now we only need one thing, which is byte of percentage. And yeah, so if we hexify that payload, so payload dot hexify dot hex, yeah, so this is basically what this 41 is. Okay, now if you go and check that out, so it is 45 5. Wait a second. I think there's a problem here. I'm supposed to be sending 44 and C8. Yes, but it's supposed to be C8, not 5C. Gotta check that exactly. Yeah, I gotta check that. There's a problem exactly. I have supposed to be setting 4408. Yeah, but I forgot something. So I think I'm a little too, I'm a little bit tired because of the other channels. We have to change them. Oh my goodness. Okay, C8. Um, We don't have to. Wait a second. Okay, just a second. Yeah, it's C8, yeah. C8 and should be just using the other one, I suppose. X 64, which is 44, I'm sorry. And we add 41, and then, yes, we just send 7f minus 2. Yeah, that's supposed to be the address that we want to write. The, the pointer to, yes, it's supposed to be that one. Yeah, now if we try that one, payload dot hexify that. Yes, now it's working well. So it's C844 and we have all of that. So basically if we try that out, what is the problem? Gotta reset that. Okay, so if we continue, I'm gonna be sending this encoded hex. Yes, and it's unlocked. Okay, that was really easy to be honest. Once you watch the for mastering vulnerability, you should be solving that directly. So yes, I hope you have learned something new, guys. Don't forget to follow me on Twitter. Don't forget to hit also the sub button. We are, as you can see, closer more to the finish of the microcorruption challenges. Yes, so have a nice day. Bye.